In the previous video, we've seen how we may model a portfolio problem into a quadratic programming. Here, we're going to look at a method called Wolfe's method to solve quadratic programming. So let's see how it works. So Wolfe's method may be used to solve quadratic programming problem in which all variables must be non-negative. So here's an example of a quadratic programming problem, and then we see that all variables here must be non-negative. So this is the general form that all inequalities are in the form of less than or equal to. And then so we also may modify this sign restrictions to become minus x less than or equals to 0, just so that we have the sign of less than or equal to for all constraints. So given the quadratic programming problem in this form, like the model number 30, we can use theorem 11 prime. So we omit the first part because it talks about the model that without the sign restrictions. So now we focus on the second part. So it says if the model is a minimization problem, and then the objective function f is a convex function, and then all the constraints g, they are all convex functions, then any point satisfying the hypothesis of theorem 10 prime is an optimal solution to this model. But before going to look at what theorem 10 prime says, let's start with this. It says that f must be a convex function, and all the constraints g, they also must be convex functions. So let's check that first before going on to theorem 10 prime. So a function is called convex if and only if all principal minors of the Hessian are non-negative. So we need to obtain the Hessian first and then check the principal minors. So this is our problem, and then let's check the z function first. So take the first derivative of z with respect to each of the variable. So with respect to x1 and then with respect to x2. And then let's take the second order derivative. So second order with respect to x1, with respect to x1, x2, x2, x1, and then with respect to x2. So all these elements we store into the Hessian matrix. So 1, 1, the 1, 1 element is that, and then this is the 1, 2 element, this is the 2, 1 element, this is the 2, 2 element of the Hessian matrix. Now that we've got the Hessian matrix, we check the principal minors. So principal minor is that the determinant of a matrix when we delete n minus I rows and then n minus I columns. So for example, if you want to have a 1 by 1 matrix, means that you need to delete 1 rows and 1 corresponding column. So for example, if you delete the second column and second row, this is your 1 by 1 matrix, and that is the principal minor. If you delete the first column and then first row, this is your principal minor. And then if you want to have a 2 by 2 matrix, means that you need to delete 0 rows and 0 column, or in other words, you just compute the determinant of the entire Hessian matrix. Okay, so the principal minors are 1, 2, so the elements in the diagonal, and then the determinant of the entire Hessian matrix, which is 1. We can see that they are all non-negative. So we may conclude that z is a convex function. Actually, we need to check all the constraints as well, but because in the quadratic programming problem, all constraints are linear, they are guaranteed that they are convex. In other words, all principal minors of the Hessian are non-negative. So G1 or the first constraint is convex, and then the G2 or the second constraint is also convex. So now that we have shown that the objective function is a convex function and all the constraints are also convex. Let's see what we can do with theorem 10 prime to solve this problem 30 here. So it says, the theorem 10 prime says that to solve this problem, we need to find the solution x bar, which means x bar 1 to up to x bar n, that satisfy all the original constraints here in the problem. And then there must exist multipliers lambda 1, lambda 2 up to mu n, such that those multipliers satisfies all these given equations. All those equations that we need to fulfill are the K-T conditions. And then we may do something to kind of simplify the conditions a little bit by noticing that because mu bar j is greater than 0, we may rewrite this equation 36 to becomes like this. So if we move this to the right hand side, and then we realize that mu j itself must be greater than or equals to 0. So this part, in other words, must be greater than or equals to 0. Okay, so in other words, to solve this model number 30, we need to find a solution that satisfies all the constraints in the original problem, and then also find all the constraints, find all the multipliers that satisfies all these K-T conditions. So we have 4 K-T conditions. Let's start from the first. So that is our problem, and we are going to create the equation or the inequality for the first K-T condition. So we just ignore the other K-T conditions for now and just focus on the first one. Okay, so the first one says that we need to take the derivative with respect to each x variable that we have. Okay, so we have x1, x2 up to xn. In our problem, we have x1 up to x2. So we need to create an inequality with respect to each of the x. So let's do it with for x1 first. So here we take the derivative of the objective function with respect to x1. So this is the first one, and then this part means that for each constraint that we have 2 constraints. We have lambda 1 and lambda 2 multiplied by the derivative of the constraint with respect to x1 in this case. Okay, so take the derivative of the objective function with respect to x1, take the derivative of the first constraint with respect to x1, multiply with lambda 1, take the derivative of the second constraint with respect to x1, multiply it with lambda 2. Okay, so this is the first derivative of z with respect to x1, and this is the derivative of the first constraint with respect to x1. Don't forget to multiply it with lambda 1, and then this is the derivative of the second constraint with respect to x1, and don't forget to multiply it with lambda 2. So that's the first K-T condition with respect to x1. Next, we are going to do the very similar thing with respect to x2. Okay, so again we focus on the first K-T condition. Now let's do the same thing with respect to x2. Take the derivative of z with respect to x2, derivative of the first constraint with respect to x2 times lambda 1, derivative of second constraint with respect to x2 times lambda 2. And this is the result, the K-T condition, the first K-T condition with respect to variable x2. So far we have completed the formulation of the K-T conditions for the first condition. With respect to each variables that we have, x1 and x2, these are the 2 inequalities that we have. Because later, basically, we will solve this problem using simplex algorithm, we need to convert this into standard form. If we recall about standard form in simplex algorithm, whenever you have the sign of greater than or equal to, you need to add this excess variables. You need to add the excess variables, and the sign is minus. So minus E1 for the first constraint, and then minus E2 for the second constraint. And then now if we look closely, you can see that this part is the first K-T condition is this one, right? That's what we did for the first K-T conditions. And then this is greater than or equals to 0. And then we put this minus E1 such that it becomes exactly equals 0. Now if you move the minus E1 to the right hand side, you have this form, right? So EJ equals to this thing on the left, and that thing on the left is this. Okay, so when we have noticed this thing, we can say that for the third constraint, we can say that the one in the square brackets here is E1 and E2, and then we need to make sure that E1 times X1 equals 0, E2 times X2 equals 0. Again, because you notice that the thing in this square bracket is exactly the same with the definition of E1 and E2. Before talking about the second and fourth constraint, let's talk about the original constraints first, that the problem obviously has to satisfy. Okay, so this is the original problem, and then remember, as I've said before, we are going to use simplex algorithm to solve this. So if you recall, the first step in simplex algorithm is checking, is there a right hand side that is negative? So here, yes, we have a right hand side that is negative. So we need to start by multiply the entire constraint with minus 1. So this is the original problem, and then we'll multiply it with minus 1, so then it becomes like this. Okay, and then from here we proceed by converting it into standard form. As usual, if you have less than or equal to, you add plus S1. If you have greater than or equal to, you put minus E2. And then you have the sign here, S1 prime, E2 prime, because it just denotes that these are the slack and excess that comes from the original constraint. Okay, so this is the complete formulation. Let's see what we've done so far. So the first two constraint is the first K-T condition in standard form. And then the next two constraints, there are original constraints in standard form. And then these two equations here, they are the third K-T conditions. Now we need to talk about the second K-T condition. So these two equations, they are the second K-T condition. Lambda times this equals 0. Now you may wonder why this thing in the square bracket equals E2 prime or S1 prime. Well, if we look at the definition of E2 prime and S1 prime from these two equations, you see that E2 prime equals 2x1 plus 3x2 minus 6. S1 prime equals 3 minus x1 minus x2. Okay, so you just move the terms to left hand side or right hand side. Now the term here inside the brackets says bi minus gix. So it is a measure of how much the difference between the availability of the constraint bi minus the amount of constraint that you actually consume gix. And you can see that that difference is exactly captured by S1 and E2. So that's why you can say lambda 2 E2 prime equals 0, lambda 1 S1 prime equals 0. And I think the sign bi minus gx or gx minus bi, like here, gx minus bi, doesn't really matter because what you want to do is to have the multiplication equals 0. So the sign doesn't really matter. Okay, so this is the second K-T condition. And finally, all variables non-negative is the how we say about the fourth K-T conditions. So now this is the complete formulation because we have seen that we have created the constraints that satisfy or satisfy all the K-T conditions, and then also satisfy the original constraints, and then everything is already in a standard form. So this is complete. Finally, we may solve the problem. We are going to use the phase 1 of the two-phase method. If you recall the two-phase simplex method, we have phase 1 and phase 2. Here we are only using the phase 1. However, because we have the complementary slackness constraints, so the complementary slackness constraints are these equations: E times X equals 0, lambda times E or lambda times S prime equals 0. We need to make sure that the solution satisfies this complementary slackness constraints. So to do that, we need to kind of modify a little bit the phase 1 method. The modification is that we would never perform a pivot that would make EI from the ith constraint and XI both basic variables. So E1 and X1, they cannot both be basic variables. E2 and X2 cannot both be basic variables. Similarly, we cannot have lambda 2 and E2 prime or lambda 1 and S1 prime to become basic variables. So when we perform the pivot, means that when we determine who becomes the entering variable, we need to be careful to make sure that these two things, they must be satisfied. So that is our formulation based on the K-T conditions and the original constraints. When we want to use the phase 1 method, if you recall, the phase 1 method has the objective of minimizing all the artificial variables. Okay, before talking about the objective, let me remind you that when you want to use the phase 2 method, anything that has a minus excess, they must be added by artificial variables. So we have A1, A2, and A2 prime. Okay, but if we have the slack variable like this, we do not need to add artificial variables. So once we have the artificial variables, we define the objective function of the phase 1 that looks like that. Minimize the sum of all artificial variables. But again, if you recall, when you want to perform the simplex method, or specifically the two-phase simplex, the artificial variables, they must become the basic variables, which cannot happen if they also appear in row 0. So what we need to do is we need to get rid of artificial variables from row 0 using the elimination. So this is what I meant. So first you move A1, A2, and A2 prime all to the left hand side. So now it looks like this: W minus A1 minus A2 minus A2 prime equals 0, because now you move everything to the left hand side. Now you want to get rid of minus A1. What you can do is you add this row 0 by 1 time the first row. Why are we doing this? Because the first row of the constraint has plus A1, so when we add them together, A1 will be removed. And then similarly in the second constraint, you have plus A2. So we can use this to get rid of the minus a2 in the row 0. And then from the third constraint, you have plus a2 prime, so we can also add this together to get rid of minus a2 prime in the row 0. You take the sum of all this thing and we have the new row 0. So if we take the sum, here's our new 0 that we can see on the table. We do not have a1, a2, and a2 prime anymore, and then the right hand side becomes 8 because 1 plus 1 plus 6 becomes 8. And then you have x1 minus x1 plus 2x1, so x1 equals 2, and so on. Another example is, for example, lambda 1. You have lambda 1 plus lambda 1, so lambda 1 equals 2. Okay, so this is your new row 0, and you are ready to perform the two-phase simplex. Specifically, I mean just the first phase of the two-phase simplex. So this is our initial table, and then remember that whenever we pick the entering variable, we need to keep in mind about this complementary slackness constraints. Okay, because the phase 1 of the two-phase method is always minimization. So here we pick the coefficient, the variable with the most positive coefficient. In this case, it is x2 with the coefficient of positive 4. So we see that e2 is not a basic variable, so it's okay to pick x2 at this point. So we pick x2 as the entering variable, and then we perform ratio test. 1 divided by negative thing here is none, and then 1 divided by 2 is 1/2, 3 divided by 1 is 3, and 6 divided by 3 is 2. And always pick the smallest ratio. And then here in this part, if you recall the simplex algorithm, you need to make it equals 1, and then the other value in that x2 column must be 0. Next, we see that we have the variable with the most positive coefficient, x1, and then we choose that to become an entering variable. So again, we check our complementary slackness. So we see that e1 is not a basic variable, so it's okay to pick x1 as the entering variable. We pick x1 as the entering variable, we perform ratio test. I don't show the ratio test results here, but you should verify that the smallest ratio is obtained in the last row, such that this position becomes our pivot. So in other words, again, in the next table, that position in x1 column must become 1, here must become 1, and all the other values in this column must become 0. And how can you do this? You perform elementary row operations. Okay. Now here, again, we pick the most positive coefficient. So here we see lambda 1 has the most positive coefficient, 12/7. However, if we notice the sign restrictions, the complementary slackness constraint, you see that lambda 1 and s1 prime, they cannot both become basic variable. Right now, s1 is a basic variable, which means that we cannot pick lambda 1 to become entering variable. Okay, we cannot choose this because s1 prime is a basic variable at this table. So we pick the next most positive variable, and we have e2 prime. So we are going to pick e2 prime as the entering variable. Again, after we pick e2 prime as the entering variable, we perform ratio test, and then based on the ratio test, we know that this is the pivot, and that position must become 1 in the next table, and 0 for all other values in that column. Okay, now we pick again the most positive coefficient. It's lambda 1 again. But then here we are allowed to pick lambda 1 because S1 prime is now a non-basic variable. Because S1 prime is a non-basic variable, we may pick lambda 1 as the entering variable. So we pick lambda 1 as the entering variable, perform ratio test, and then perform elementary row operations. And this is our optimal table, because you see that we do not have any variable with positive coefficients in row 0 anymore. And then at the end of the phase 1 simplex, if we have a right-hand side on the row 0 equals 0, it means that we have reached the optimal solution. So we stop our calculation here. So this is our optimal table, and we may read the solution like this. x1 equals 9 over 5, x2 equals 6 over 5, lambda 1 equals 2 over 5, e2 prime equals 6 over 5. All other variables equal 0 because they are all non-basic variables. If we look at our original problem, we may see that S1 primes equals 0, means that we exactly use the resources of this, whatever this is. We consume all the amount of these 3 units of that resource. Because we consume everything that we have, it means that it will be valuable if we get an additional unit of this resource. That's why lambda 1 is positive. It's kind of a shadow price, lambda 1. It means that how much you are willing to pay for an additional unit of resource. Right? Because right now you consume all the resource that you have for the first constraint. You would like to pay for additional unit because you really need that kind of resource. For the second constraint, you don't consume everything. You still have excess, right? E2 prime is 6 over 5. That's why you are not willing to pay for additional unit of that resource. That's why lambda 2 equals 0. It is a non-basic variable. The logic is that if you don't consume all the resource that you have, all the units of the resource that you have, why would you want to pay for an additional, right? So that's why lambda 2 equals 0. So this is the optimal solution for our problem. So the final note is that Wolfe method is guaranteed to obtain the optimal solution if all leading principal minors of the objective function's Hessian are positive. So in other words, the objective function is a convex function, which we have checked at the beginning before we solved the problem. When it is not a convex function, Wolfe's method may not converge in a finite number of pivots. So that's the end of this video of how we can use the Wolfe's method to solve the quadratic programming problem. Thank you and see you on the next one.